idea is not to teach you about finite element method itself, but rather talk about its application, right? So I'm going to start with totally the other end of the problem, how it is used and so on. And I expect you to know what the method is and how it works. So I'm not going to teach that. So this is a structure. Have you seen a structure like this? Yeah, exactly. And structure could be any form. So we're talking about a structure, it could be any regular thing. Building, bridge, a stone, this one. Doesn't matter what it is. It's a structure, that means it's a physical block of things and supported at some locations. And if you have any piece of a continuum of matter, what happens to it? It is excited. It is excited, that means something is always trying to change it. That could be the loads, vibrations, settlement, temperature changes. Even if nothing, there could be support settlement. Or temperature may be changing daily, morning, evening. So there is always something going on with the structure. Maybe vibrations from people walking around, from cars moving around, earthquake, wind, whatever. So generally there is some kind of excitation. So we put all of these things together and call it excitation. So the structure is always being excited. So when you excite something, what happens to it? Basically, if you excite something, it will respond. So when you have excitation, there is always a response. If somebody is not responding, it's probably dead, right? So for structure, excitation, you get response. And what is the response from a structure? Displacement, strains, stresses, stress resultants, forces, something. That is the way the structure will respond. Right? When somebody is patient, they're looking at the doctors are coming and oh, this patient is not responding. They look at the pulse, they look at some vital indicators, and if those indicators are not there, that means, right? So structure is exactly the same. They also have those vital indicators. Those vital indicators are displacement, strain, stresses. We just know how to measure them. So if the structure is not responding, actually it's not even possible, because there is always some excitation. So as long as the structure is there, it will have some response. And our job is basically what? Wait first. How does a structure respond? Typically, on a very simple way. Structure is like a big spring. If you apply some excitation to the structure, let's say it is producing a response, and right now I'm saying load is a force, and response I'm saying is a deformation U. Just one of the things, I'm just taking one example. Then there is a relationship between response and excitation, right? If I increase this, this will increase. If I decrease this, this will decrease. 0, 0. So there is some kind of a apparent relationship between them. And sometimes we call it a linear spring relationship. That means F is equal to KU, correct? So there is some constant here that if you apply force 1, the displacement could be 1 or 2 or 0.5. And that will depend on the factor K, which is a kind of a scaling factor for the relationship between force and deformation. And that scaling factor K is a property of the structure. So if the structure has high stiffness, response will be small. If the structure has small stiffness, response will be large. That means the response to excitation depends on the structure itself, the properties of the structure itself, on a very basic level. And this is called a linear response equation. That means you increase the force and the response increases proportionately with no limit. And if you decrease the force, the response becomes small, and if the force is 0, displacement becomes 0. right? That is what we know, that's what we have been taught, that's what we think. But imagine now a frame like this. Okay, a frame like this. F is here, U is here, this is 3 meter, this is 5 meter. And let's say K is equal to 1 for this case. To system K is equal to 1. If I apply force equal to 10, what is U? If I apply force equal to 10 ton, let's say ton, let's say the units are ton and displacement is centimeter. Okay. So 1 ton, 1 centimeter, because K is equal to 1 from this equation. Correct? Force is 10 centimeter. Force is 100 centimeter. Force is 1000 centimeter. If force is 1 million centimeter. Can you imagine a frame with a 3 meter height have a displacement of 1 million centimeter? Right? Going all the way to the moon maybe? So something must be wrong here, because it cannot be true, because it's impossible. So this means this elastic relationship between the structure and this one that we have been studying all the time is not actually going to work for us, because it does not take into account many things, because this will not work after some time, and also the K will not be the same after some time. K will change. So that brings us to, and also just imagine if I apply this force slowly or if I apply it suddenly, do you think the response will be the same? Right? But this doesn't tell me that whether this force is slow or fast. It just tells me 10 again. But actually we know from intuition that if I apply 10 force like this or I apply 10 like this, the response will be different. So that means there are things that we are not including in that system that need to be included. Which brings us to the full picture. The full picture of the structure is that excitation could be static, which I told you, slowly applied, right? Static means very gradually slow or standing force, or it could be dynamic, applied with a time component, right? Very fast or changing with time. So if the force is changing with time rapidly, it's a dynamic force. If the force is not changing with time or is slowly changing, it's a static force. So the excitation, whatever that is, could be either static or dynamic, and that will impact the response. Correct? The structure itself could be elastic. That means you pull it, and when you release the force, it comes back. Or you push it and you release the force, it doesn't come back. And normally, many structures, if you push it too hard, it will break and it will not come back. So that means the structure may be elastic or it could be inelastic. That means it will not rebound back, it will not come back. Alright? And the response could be linear. That means the excitation and response could be related linearly with a constant factor, or the response may be non-linear, may change depending upon the displacement and force values. It may not be the same, it may change. In the beginning, K was 1, then K become 0.75, and K became 0.25, or K become 1.25 after some time. So that means the response and excitation relationship may not be linear, could be non-linear. So these are the 6 possibilities that can happen. So how many possible relations are there between these quantities now? So there are 8 possibilities of this thing happening. It could be static, elastic, linear, static, elastic, non-linear, dynamic, elastic, linear, dynamic, elastic, non-linear, and so on, right? So there are 8 possibilities for us to have in this combination. That means there are 8 ways that the structure could behave and that we can analyze. Normally, people only do this static, elastic, linear. So that's why we call it linear static analysis, linear elastic static analysis. And that's what most people will do, most codes will do, except the new ones which are coming up now. But that is not enough, as you can see, that the linear, elastic, static response is not going to be enough. And obviously, we are going to do, and the highest one, the most complicated one, the complete one is dynamic, inelastic, non-linear. And that is what the real structure will be doing. And that is what we should be trying to do. Right? So, the finite element itself gives us the opportunity to do all of that. So 8 types of equilibrium equations are possible, as I mentioned, right? Later we will get an equation to do that. So the point is, why do we need analysis? The reason we need the analysis is because we want to determine the excitation, we want to determine the response to the excitation. Why do we need to determine the response to the excitation? So we control it. Control it means if the deflection is too much, we don't like it, we have to control it. And that part of controlling is the design part. So calculating the response to the excitation is the analysis part, and to control it is the design part. So you can calculate the response of anything, whether it is going to work or it doesn't. Like for example, I told you, you can calculate the displacement for 1 million ton, which will come out to be 1 million centimeter. But that is not design. Design will not allow you to do that. Design will say, oh, no. You cannot have more than 4 centimeter displacement for this frame. So stop. So analysis can give you any number, acceptable or not acceptable. But design makes sure that it is acceptable. So design and analysis always go in hand. This is the basic partial differential equation of equilibrium, which links the displacement. It's the equilibrium of the body, external forces, internal, it's a balance of energy, balance of everything, equilibrium. If the body is standing, this equation, partial differential equation, must satisfy in terms of the displacement, strains, energy, and force and work done outside, and everything. So you can relate it in many ways. But basically, it's saying that the external and internal, this is an excitation PV, and internal body strains, displacements should be equal, right? 0, net should be 0. If it is standing still, not applicable to a moving car, but it is applicable to a standing structure, right? So this displacement, after some time, the structure must become equilibrium after deformed. See, originally the structure is stationary and undeformed. When you apply excitation, it is deformed as a response, and after that becomes stationary again. Important to note that it's not moving. If it's moving, it is not our system. It's a mechanical system. So there could be a net displacement here if it is moving, right? Not 0. So this equation is quite good, but I'm sure if I give you will not be happy solving this partial differential equation. Not only that, it is only possible to solve it for very simple structures like one beam, one column, one slab, simple loading, simple boundary. When things become complicated, this equation becomes too difficult to formulate and solve. So practically, mathematics, pure mathematics, will not help us in the determination of the response in this form. So we need to find an alternate way of doing things, right? We still need to solve this equation, but not as an entirety for the structure like this. It's just too complicated. Even to form this equation, forget about analysis. And instead of the real structure, we create a model of a structure, because real structure is too complex. So we say, okay, I'm going to simplify it, and this is going to be my model. And after that, we find an easier way to determine the response of this simplified model. So we are now doing two things. We are simplifying the analysis, and we are also simplifying the structure so that we can solve this problem. So then the excitation and loads are applied not to the structure, to the model. And the response that you get is for the model, not for the structure. And this is one most important thing that you need to realize. Don't say, I am analyzing the structure. You can never do that. You are always analyzing model of the structure. So if your model is not good, response is not good. I mean, the response may be very good for the model, but it may have no relationship with the structure. So the structure and model have to be very good, and then this analysis has to. You may get from your analysis or SAP or whatever 10 digits of accuracy. It means nothing. It means nothing if your model is not right. Right? So accuracy and correctness are two different things. Your analysis may be very accurate, it may not be correct. Highly accurate numbers, everything is very, equations were solved correctly, but it may not be correct. It may be incorrect even though it's very accurate. Can you understand the difference between the two? Right? So do not confuse accuracy with correctness. Correctness can be done without calculations, and high amount of computations can lead to incorrect results. So what you need to do is accuracy and correct, combine them together. So why do we need modeling? Number one, real structure cannot be analyzed for two reasons. One is that real structure does not exist at the time that you are trying to analyze it. It doesn't even exist. So how can you analyze a thing which doesn't even exist yet? So that means in any case, you're dealing with a model of a structure that will be built later. If you want a response of a real structure, make it first and then test it. And that's what you do in the lab. You make a beam, you apply the load, that is the response of a structure. Anything else is just a model and an analysis. You remember your previous class, you had, you went and you tested and you made a line diagram and applied the load. That line diagram is not a beam, it's a model of a beam. Because beam is not line diagram. Beam is this, right? So physical beam and your model were very different, right? At that time you didn't realize, you didn't care, now you will care the difference between the real structure and the model of a structure, right? So first problem is that we cannot analyze the real structures. If we want the response, we just have to test it. B, we can only analyze model of the structure. So what do we need? We need tools to model the structure, and then we need tools to determine the response of the model. So modeling and analysis are two distinct steps. Sometimes they are combined, sometimes not. So ability to model is one thing, and do the analysis is another thing. Right? So as I was saying, this solid, or this slide I borrowed from Professor Watson when he used to teach us 30 something years. Okay. I'm still using his slide because it still conveys the meaning. 3D continuum model governed by partial differential equation, which I showed you. And the structure that we look at, we simplified already, because this may have walls and windows and door frames and other things which are not here. So already we removed many parts of the structure to make it a continuum model of the structure, which is not really complete structure still, right? And this is still used by partial differential or total equilibrium equations. But what we really analyze typically is the discrete model of a structure. We say this is a beam, this is a column, this is a node, they are connected here, line elements, lines. We really go very far from reality. And how far we go from that reality to here is the modeling issue, right? And very accurate model again does not mean it will give you good results. We will talk about that a little bit later. On a very simple level, coming back to what you are studying with Dr. Panchit now, this is the object that we want to analyze. You may divide it into triangular elements like this and put the node there, combine them, and you get a mesh, right? So if you want to analyze, determine the response of an object like that, right? Because there is no element like that, maybe you convert that into elements, mesh, and then put the nodes and then calculate the response. So that is the way we work. We take something which is complicated, we break it down until we come to our elements that we know. Okay? This whole process is called discretization and modeling. And then using that process you can create all these nice complicated forms can be converted into simple elements and the response can be determined. Basically, the idea is that break them down into the elements that we know. So all of them are converted into simpler elements which are very few, right? And then we can determine the response and we can understand what's going on. Even human heart, these days people are modeling human heart. But, doctors, they say when you study in the beginning, you say you want to go to medical or you want to go to engineering. If you go to medical, you don't need to worry about mathematics. It's totally untrue. Nobody is using more mathematics and more computing and more computer graphics and more computation than doctors these days. Maximum application of high-end applications of finite element are actually being done by the doctors, not by us anymore. So doctors have to be computer scientists, they have to be computer graphics people, they have to be finite element people. Right, so the reason I put this together is that this is a big sewage water tank underground and this is the heart. The two are actually the same. This has water inside with concrete boundaries. This has blood inside with tissue boundaries. Both finite element can handle. Only you know how to model and then the software will be the same. So the trick is modeling. If you know how to model something, finite element doesn't care what the original object is. It doesn't even know. At the finite element level, it doesn't know what you are trying to solve. It just has a bunch of equations it's going to turn into. It doesn't know at all. Right? So the important point is modeling. How do you do the modeling? And then that's why we divide the finite element analysis into these two parts. Finite element analysis, a discretized solution to a continuum problem using finite element method. So the analysis is dividing the problem into small pieces and then use finite element method. It didn't say anything about structure. Did I say anything about structures? Nothing. And finite element method is nothing more than a numerical way to solve the differential equation that we solve. Nothing more than that. It's simple. The definition is extremely simple. We are just trying to solve the same partial differential equation that I showed you earlier. Instead of doing it mathematically, we do it numerically because computers are fast at that, right? So that's it. As you can see, this can be applied to anything. All you need is this tool and that tool. This is you, this is software. Sometimes they now get mixed up. We'll talk about that. So, from classical solution for the actual structure, which is governed by partial differential equation, we do some tricks, which Dr. Panchit is teaching you, which you should learn from him, how to do this dotted line. This is not my class. This dotted line is Dr. Panchit's class, which converts that into that. You use assumptions, equilibrium, stress strain law, compatibility, energy balance, whatever, virtual energy, something. And then finally, you convert that into this, and this is what you solve. So basically, the partial differential equation is converted into an algebraic equation. No matter how complicated the partial differential equation this side is, on the other side, you always get an algebraic equation. And the algebraic equations can be solved by using the numerical techniques. In fact, there should be a problem here because we are supposed to know K, right? We are supposed to know the loads, capital R, and response small r can be calculated. So R, small r is equal to R divided by K, correct? Just now we have seen. So if you want to calculate the response, you divide the force by the, if you want to calculate the displacement, you do that, right? So, yeah, correct. So you can calculate from that. So basically, it's just a matter of, the problem in the real structure is that there is not one displacement, there is not one stiffness, there is not one force. Too many things are happening. Like in that frame, there are 3 beams, 2 columns, one. So when I say K is equal to 1, actually that should not be anything, because stiffness of columns will be different, stiffness of beams will be different. So for me to say that the structure has a K equal to 1, I'm talking about the summation of the stiffness of all the elements there. So that is the sum here, but individual stiffness need to be determined and added up together to get the structure stiffness. And I think you will learn all of that, or you have learned all of that. So for me, for our subject, this is what I'm concerned with. I'm concerned with how to prepare the model, how to assign boundary conditions, how to apply the loads. That is our concern. And after that, perform the calculations is not my concern. Generate stiffness matrix, connect elements, assemble loads into a load vector, impose support conditions, solve equations. This one is not my concern. That is Dr. Panchit's concern, or the software that has already been developed. Right? And then finally, post-process is my concern and your concern. What do you do with the results that you get? Like displacement you got 10 centimeter, what do you do with that? How do you understand that displacement? What is the meaning of that displacement? Right? That is important. So for me, creating the model, applying the loads is important. Getting the response, I skip the step in between, and then processing the response is important. Correct? So this is the process. Evaluate the real structure, look at it, see what it is, what are you going to do with it, is it a beam, a hard, or a chips, or what? Evaluate it, what is it, right? Create a model, a structural model first, remove things that you don't want in that structure. Like for example, this room, you want a model, there's a window there, do you want it in a model or not? False ceiling, do you want it or not? Lighting, this load of this projector, board, door, clock, everything is here, right? So you have to then decide, okay, this is a real structure, but I'm going to remove all of this. My structure model will not have these things, but you should know why not. For example, partition walls, are you going to have them or not? Windows, are you going to have them or not? If not, why not? And if yes, why? So those are the critical decisions. Once you make that, then you convert that into a finite element mesh, discretize it into elements, small pieces, then solve the model, then interpret the results, and physical significance of those results. What does it mean to have 10 centimeter displacement? What will it do to me? Will it break my walls? Will it break the window or not? Can I accept it? Right? The vibration you calculate, is it acceptable or not? What does it mean? So the physical, so these are the steps you need to do as an engineer. Now, here is what is happening. Engineer, software engineer. You start this process, you create the model, structural model, and then software can help you discretize it. Orange, you and software work together. Solve, you cannot do anything. You can have coffee there at that time or go home, wait for the computer to finish its run and come back. There's nothing you can do at that time, right? Results come back, you start inputting, program can help you. Graphics, display, animation, and so on. So here you need to be here you can be at home, not at the computer. Here you have to be at the workstation for these tasks. Right? This one you can do independently without the computer. So that's the whole thing about finite element analysis, finite element method, and using finite element. So for our projects, we are going to take the real building that we had given you. You are going to come up with a model. Before that, you need sizing. Then you are going to use ETAB to discretize it, solve it, get the results, and then make a report and convince me that you are right. That's it. Right? Now we come to important things. As you know very well, that the most important, most difficult, most complicated part of the finite element modeling, which separates one field from the other, is what? Material. Human heart versus concrete. So if you understand the difference between a flesh membrane, right, or a tissue, and concrete, and how to model that material, and how to model the behavior of that material, that is the key. Everything else is common, right? So most difficult part and most incomplete understanding that we have in our analysis is still related to that we do not understand materials very well, and we do not model them very well. We cannot model them very well. That it is just too complicated. Imagine concrete. You say it's concrete, but concrete is not really a material. It is made from cement paste, sand, and stone. Correct? So concrete, when we say concrete is a material, is actually an incorrect statement. Inside you have three things put together. And if you go to the next level, there are gaps between even the material, voids, the bond between aggregate and material paste, interlocking between the aggregate, shape of the aggregate. So if you keep on going inside, you will find that this is a very, very complicated problem. Same is the case with any material that you take, except maybe steel, which is quite simple, relatively simple. Aluminium, metals are relatively simple compared to other materials. But the main issue is, how do you model the material and what represents a material? What is the difference between material? We talked about it. The stress strain curve is one way to distinguish material from the others. Full three-dimensional stress strain matrix is the only way that a material can be defined for a computer program, right? Stress strain curve plus the matrix linking the stress and strain is the only way that you. So the trick is, how do you convert a material into a matrix? And for that, we need to understand the first thing, local coordinates. Like reinforced concrete has a rebar in it, right? And then concrete. So every material, and if I can put the concrete like this, or I can put the concrete like this. So if I put the concrete like this and apply the force along the bar, different If I rotate and rebar in this direction and load in this direction, different. That means whatever is the material, the local direction of that material is important, local axis. That means the properties of the material are defined on the local axis of the material in which it was originally tested. But you can put it in any way, but it will behave according to its local axis. So the properties have to be transformed from local to global and so on. So understanding of the local coordinate system of the material is very important. National coordinate or local coordinates is very important. That's the first thing. Each material has its own material local coordinate system, which is used to define the elastic and thermal properties. Right? So properties are defined on the basis of the local coordinate system of the material. The axis of the material local coordinate system are denoted by 1, 2, 3 or theta or some other symbol, doesn't matter. But it's important that the local coordinates of the material may not be the coordinates of the member, and member coordinate may not be the coordinates of the structure. So every time a coordinate is changed from one to the other, what do you need? What do you need? Come on, people. Transformation matrices. Transformation from one to the other coordinate system, right? So you need those transformations all the time. T matrix. So you need a relationship between local coordinates and next coordinates and next coordinates and next coordinates. The material coordinate system is aligned with the local coordinate system of each element. So element has its own local coordinates. So material has its coordinate. Let's say rebar has its own local coordinate. It may be along the beam or it may be vertical to the beam. So then it is different. So rebars may be along the beam, ties may be perpendicular to the beam. So we need to make sure that we understand the relationship between the material and the element. And the element may be horizontal, vertical or inclined. So it has another level of coordinates. So this kind of understanding is very important if we are going to go into the detail. But normally, when you model a beam, you don't even model the rebars in the beam. You just model the concrete, right? And you don't care about local coordinates of the concrete. You only care about the local coordinates of the element because we are going to represent it as a line. So everything is sort of merged into one element. So this is only important for orthotropic and anisotropic materials. I will talk about that, or maybe you already know what it is. If not, we will discuss. So for simple models, this information is not important because we don't even have the ability to model this. This is how the coordinate systems will be. 1, 2, 3, and then local coordinates on each face for each stress component, and so on and so forth. So this block is every particle of the material is presented like that, and there are faces, there are stresses on each face. You know about all of this, I hope. So elastic mechanical properties relate the behavior of the stress and strain, we know that. And then stresses are defined as forces per unit area. Not all stress component exists in every element, we know that also. So we talked about this last time in our course, and this is the matrix we arrive when we see a lot of zeros here. That means there's no relationship between certain stresses together with each other, which is good for us. But not always true for, this is only true for isotropic material. One type of material. What is an isotropic material, by the way?
Same properties, no direction.
Sorry?
Same properties, one direction.
Yeah, basically one direction only. There is no more direction. Isotropic has only one direction. We ignore all other directions. Basically, keep only one direction. So isotropic material and 2D isotropic material, we go into even more simpler forms. So this is the definition, please read that. understand that. Orthotropic. What is an orthotropic? We also talked about it a little bit. Now it's time to understand it a little bit more detail. Orthotropic material. We haven't studied too much about orthotropic materials. Orthotropic materials are in which the properties in two perpendicular directions are not the same. Let's say you are modeling a slab, right? And there's a concrete in that slab. Now the concrete, not concrete, the whole concrete in that slab, reinforced concrete in that slab is orthotropic. Because in one direction may be more reinforcement than the other direction. So in one direction its properties will be different than in the other direction, right? Just to give you a very simple idea. Then other things can be like that. So if you model that slab as isotropic, you are wrong because you are ignoring the difference in properties. Similarly, hollow core slab, for example, in the direction of the cores, distant, different, other direction, different. Precast panel slab, totally different. So it's also the way material is used, right? Anisotropic. Orthotropic has one property though. The two direction properties are uncoupled, independent of each other. Anisotropic material is where the properties in each direction, three directions are different, but they are also coupled. These are most complicated materials. In fact, most materials are like this. We just don't model them to that level. Let's say we take a beam. Normally we model the beam as a line element. So we have to assign, we have no choice but to assign isotropic properties to that beam because it doesn't have the ability to model in the other two directions. So it has only one direction. So the properties of the materials, no matter which material we are using, the properties have to be only isotropic. So it's not that materials have different properties, it is our modeling of those properties that makes a difference. Same concrete, when we put in a slab, becomes orthotropic. Same concrete, when I put in a dam, becomes anisotropic. So it's not so much the material, but the ability to model the material in different dimensions. It's a one-dimensional model, has to be isotropic. Two-dimensional model, orthotropic. Three-dimensional model, anisotropic. Right? So that means it's about the modeling again. It's not so much about the material. I mentioned last time also temperature dependent properties. Most of the properties of material are dependent on temperature. Actually, they are also dependent on strain. They are also dependent on many things. They are non-linear. We have talked about that with stress and curve and everything. So, but now this becomes quite important, especially when you model the materials orthotropic or anisotropic, then the temperature dependency becomes very important. That's why in a modeling of a dam, the temperature variation, heat of hydration becomes very critical. You know, when you pour concrete and it gradually cools down, center part is still hot, outside cools down, that temperature variation becomes a major issue in dams and big concrete blocks, which creates huge cracking if you do not do the analysis for temperature dependent properties using anisotropic modeling, right? So there are problems that we have to consider all of that. Now let's come to slightly higher level issue. Material, as we know that it's okay, it's a difficult thing, but we must just remember three important things. The ability to model isotropic, orthotropic and anisotropic materials, right? If you're using an element which is only one-dimensional, you have no choice but to use isotropic, two-dimensional, orthotropic, three-dimensional, anisotropic. Okay? Now let's come to the geometry. Starting that from that slide. Now the question is here. How do I do this and how do I do this from here to here? How many ways there are for me to do that? Because you can argue that from here to here, instead of using this and this, why don't you divide this into many triangles, right? And keep the geometry of the member. Why don't you convert that into a line? Why don't you even remove the walls? Why don't you model the windows and walls inside? Right? So, the decisions to simplify the models becomes very important. And let's try to understand what is the logic behind these. Continuum versus structure. Continuum is something that goes in all directions. For example, this building that you're sitting goes down and sits on foundations. Foundations sit on soil. Soil continues everywhere, right? Where do you stop modeling the building? Some people stop modeling at the top of the foundation. Some people stop modeling at the ground level. Some people go to the footing, they also model the footing and then stop. They cannot see the soil. And some people model the soil also. And then the question is, how far are you going to go? Keep modeling the soil, right? Actually, you can go very far. And in London, if you construct a new building, you actually have to model one block of the city of the soil and all the buildings on it to prove that your building is not going to have any detrimental effect on other buildings. Because buildings are already constructed. If you put a building there, you're modifying the stress state of the soil. So what happened to the other buildings? So you have to prove that your building will actually not create any problem for the building. So you have to model not only your building, but it is a building and the soil, and then you have to model the whole block and then to a certain depth. So don't assume that everybody is doing what you're doing, right? There is a whole big theory of half space modeling that we used to study from Professor Bissett in solid mechanics. We don't teach that anymore here, but we used to study a lot about continuum mechanics. We used to have a subject called continuum mechanics, solid mechanics. We don't teach it anymore because now the computers have kind of taken over. But that was very important subject to model, to analyze the continuum as it is, not structure but continuum, right? So now we say that continuum is something that goes everywhere, but structure is somewhere that we define the boundary. That this is my structure and I'm going to only focus on this part of the continuum. And within the structure, we also have the habit of dividing further by name of the objects. We say this is my slab, this is beam, this is column, this is footing. Why? And last time we already talked about this is column, this is beam. What is this? Right? Or what is this? Or what is this? This is a beam, and what about little bit inclined? What is it? Inclined beam? And what is this? Vertical column? Inclined column? Then what happened? Right? Same is the case with everything. If it's a slab, it's a slab. If I put it on a soil, it becomes a footing. Right? So these are very arbitrary distinctions. From the finite element point of view, they don't matter. Right? But we have them. Then physical members, so all of them actually can be represented in an identical manner. There is no difference in finite element analysis between a slab and a footing, or a beam, or a column, or a truss. Right? They are all the same. So basically, how do we simplify this problem? For our convenience, we simplify it by using this one. You have seen this slide before also. Correct? You remember, continuum, regular solid, plate shell, beam. When we talk about, I told you that I will talk about this the next course. Now is the time that we talk about the difference between this one. So we say, okay, to make it simple, make our life simple, our modeling simple, we will make the following decisions. We will look at the structure or the element that we are modeling, and if it is in such a way that all three dimensions are nearly same order, 3 meter by 2 meter by 4 meter, we will call it a solid, and we will model it as a solid object using anisotropic materials and stuff like that. If one of the dimension is very small compared to the other two, we will call it plate, shell or slab, and we will model it by a 2D element. And if two dimensions are very small compared to the third dimension, we will call it a beam or one line element. So we will only model one degree. So line element, area element, volume element. So that's it. We basically have these three options of discretizing our structure. We can discretize our structure either using a solid elements, or using plate shell membrane elements, or using beam type of elements. That's it. Can you think of another one? There is one more which I have not told you, because I should leave something for you also. One more element we need, one more type of element we need. I have put this phone here and I'm trying to slide it, right? And the phone, I cannot slide it. There's something preventing me from sliding this phone. I can lift it up, I can put it down, I can slide it, right? How do I model this phone? What do I do? I can model, okay, looking at this, I can model the legs by using beam element. I can model the top of the table by using plate or shell element, right? Correct? I can model my phone maybe like a solid or like a shell element, okay, depend on me. But something is missing, because when I slide it, I can't slide it. And when I lift it up, I can lift it up but I cannot push down. So how do I model this together? Contact. We need a contact element, invisible element that connects two things together, which does not really exist. It's a behavior element. It doesn't exist physically, but we need it, because a lot of the modeling behavior we also need to include. So actually I need an element to connect this together, and that element will be called a contact element. We will talk about this later. How do we represent a contact element, right? So in addition to the physical elements, you also need what we call behavior elements, which do not exist, but they are needed to complete the structure behavior. All right? So basic categories of elements are 1D, 2D and 3D. That's it. Many people confuse the type of element with the modeling space. Modeling space is how you are going to represent your structure. Nothing can be represented in 1D, right? 1D means zero space. It doesn't exist. So you don't do 1D modeling. To model structure, you need at least two-dimensional model or a three-dimensional model, of course. Real structures are never in any other than 3D. So if you say, I'm analyzing a 3D structure, 2D structure, sorry, 2D structures do not exist. Structures are always 3D. We are living in a three-dimensional space. We can model it in 2D, but don't say the structure is 2D. You choose to ignore one dimension for any number of reasons, but it doesn't mean that it disappeared, right? So 1D element can exist in 2D space or 3D space. 2D element can exist in 2D space or 3D space. 3D element can only exist in 3D space, obviously, right? So can be used in 2D and 3D model, 1D, 2D or 3D model. Now 1D models are theoretically possible, point models. But what do you do with the point? So 3 types of element can be combined to create all types of real structures. Using 2D elements in a 3D space, using 1D element in a 2D space, using 1D element in 2D space, using 1D and 2D element in a 3D space, using 2D element in a 3D space, and so on and so forth. Solid elements using in 3D space, solid elements using in 3D space. But interesting, what is interesting here is this. This is an eye girder. I could have modeled this eye girder using a one-dimensional element as a line, just like I did here maybe, or it could be a solid element. Similarly, this could have been a solid element or a shell element. So the choice between using the element, so for a beam, solid beam, and this one for example, I could use a line element, right? Or I could mesh it into small solid elements to model it exactly. Mechanical engineers have almost always used solid modeling for their objects. Civil engineers, on the other hand, have traditionally used line element for their modeling, which is so far from reality, right? So I would say structural engineers, civil engineers who invented finite element method are the least qualified people right now to use it. They have lost their understanding and ability to. We use the simplest things. Other people are using really complicated, sophisticated ways. We are far behind them now in terms of how we model things. We really simplify things too much in the name of simplicity, in the name of approximation, in the name of whatever, right? Also, we don't get paid much. Another reason is that our structures are not repeated much. And that is what we are talking about. We are doing what we call macro modeling most of the time. That means we cannot afford to model everything. For example, we cannot afford to model every bolt and connection and every weld and every small detail in this thing. We will only be able to model overall shell and the frame by using line element, and we will put a connection with some behavior mechanism. This is called a macro model, in which you only model the overall geometry. Thickness is not modeled, connections are not modeled, individual welding is not modeled, bolts are not modeled. We just assume them to be some kind of a connection, and later we design them, but we don't put them in a model. So this is relatively easy, is inexpensive, and it is good for big structures. And then we can come down and then we can do some design later. Contrary, and this can be simple, linear elastic sometimes can work here because we're not even modeling anything. Most materials are simplified. Micro models, and within that, our choices are very easy. Not so easy, but okay, simple. For example, this table we were just talking about. If you want to model this table in finite element, I say, please analyze this table in ETABS. You would say, this guy's funny. Why does he want me to analyze a table in ETABS? Because it's actually building 4 columns and 1 slab, right? So we could model this by using solid elements, 3D elements, divide everything properly with everything in detail, or I can model the columns by 1D element and top as a 2D element, or I can convert that into equivalent beam. I can say part of this is like a beam with 4 beams with so much thickness, right? That's how you people do it. Or I can say, no, actually this is too symmetrical. If I model only half, it will be fine. I don't need the full one because the other side is exactly the same, right? Or you can say, no, I don't care about the legs. I will replace them by supports. I'm only interested in the top, right? So you can model a grid plate element. So you can see from here that a simple table has that many choices. Simple question, which one is correct model? Think about this. Tell me the answer next time. We'll stop here.